All right, welcome Calc 3 students. We're going to be looking at 2.2b, and this is vectors in 3D. So this continues on our graphing in 3D work. This one's going to be pretty short because it kind of just builds upon that previous section or that previous video. So what I'm going to do is I've got kind of a shorthand way of doing my graphing. If you kind of like draw a line straight down and then you create kind of like the corner of a room, you can actually create a graph that gives you the positive axes for three-dimensional space. Okay, so if you only want to think about it, it's not really a quadrant. I guess it's called an octant because there's 8 different spaces on a three-dimensional axis. This is the positive octant. We might think about it that way. And so let's say, for example, that what I want to do is I want to, I'm going to write the vector given by, 2, 3, negative 1, and so that's my initial point. Not 2, 3, negative 1, but 2, 3, 1, excuse me. And 5, 2, 4, and that'll be my terminal point. So I'll start at 2, 3, 1, and remember, here's your x-axis, here's your y-axis, and here's your z. Okay, using that right-hand rule. So we've got 2, and then we'll go 1, 2, and then 3, and then we go up 1. So there's 2, 3, 1. There's our initial point, 2, 3, 1. And then we got 5, 2, 4. Okay, so 5, 2, 4, that's 1, 2, 3, 4, 5. And then we'll go over 2 in the positive y direction, 2, and then up 4. So that's going to be, let's see, it's about this much, at least according to what I've given. So let's say it goes right about up to there. Okay, and what we'll do is we'll connect. Here's the direction of our vector. Okay, that's what it does. Okay, and there's that vector. Okay, and we're going to write it first in standard component form, or component form, or as a standard position vector. And so what that's going to look like is we're going to just go in and we're first going to give our brackets just like we did before. We'll call this V. And so V is going to equal, we'll go in, we'll subtract 5 minus 2. That's my x's, subtracted my x's. Subtract my y's, so 2 minus 3. Okay, and then subtract my z's, 4 minus 1. And so in component form, it's going to be 3, negative 1, 3. And that's the component form of the vector. So if you rewrite that, it's v equals, and it'll be x2 minus x1, y2 minus y1, and z2 minus z1. And there you are, standard component form. Now, if we want to write that vector or draw that vector, I'm actually going to have to give myself a little bit of a negative y-axis, because notice I'm going to have a negative 1 here, but that'll be 1, 2, 3, 3 in the x direction, negative 1 in the y direction, okay, and then we'll go up 1, 2, 3. So this ends up being that same vector, but as a standard position vector. Tricky thing about looking in 3 dimensions is like it's hard to tell that those two vectors are actually in the same direction. And especially because my graph isn't perfect. All right, if it was perfect, you'd probably be like, or like a true 3-dimensional graph, you'd probably be able to see it. But basically those two vectors, the one given by an initial point of 2, 3, 1 and a terminal point of 5, 2, 4 and 3, negative 1, 3 are both in the same direction and they have the same magnitude. Okay, so they're the same vector. All right, let's try this again. Okay, there's the graphing of our vector. So now, and that's basically how they're going to work. Let's do this again. And in this case, I'll actually draw out more x, more y, because we're going to have some negative ones. And here's a z. Okay, and so we'll have my initial point as being negative 1, 2, 0. And my terminal point as 4, -1, -2. Okay? And I'm just going to imagine what we can do is we can, again, there's our x-axis, there's the y-axis, kind of do the same thing along the negative values. There we go. And there's our z-axis. And so -1, so -1 in the x, 2, 0. So there's our initial point. Call that IP, the initial point. And then 4, 1, 2, 3, 4. -1, so we'll go -1, and then down 2. So there's our second point. And so there's our directed line segment, or our vector. Okay? Writing it in standard component form. Okay, and that's probably the easiest way because it also gives you the standard positional vector. We're going to get -1 minus 4, or, well, why don't we do it the other way around? We'll do 4 minus -1. Yep, that's right, because our initial point is the -1. And then -1 minus 2, okay, and then 0 minus -2. And so that's then 5, -3, +2. And that is now the standard position vector. So we'll go 1, 2, 3, 4, 5, -3, 1, 2, 3, and then up 2, 1, 2. Okay? And you kind of see, I mean, it's a little bit difficult because my graph isn't perfect, but essentially those two are going to have the same position and the same direction. Okay, there we are. Something to remember that's actually kind of important here is to make sure that, notice that our x1 here is our initial point. Okay, the one that's being subtracted is that initial point, and then our terminal point is our x2. Okay, should you switch it around, you're actually going to end up with the negative values. You're going to end up with one in the exact opposite direction. And so that could be a little problematic. Well, that could be terribly problematic because it's not exactly the same vector. Okay, it's actually a different vector. It's going the opposite direction. So now let's look at standard unit vectors. If you remember from our 2D lecture, in that one we had I and j, okay, and they were represented by 1, 0, and 0, 1. They allowed us to actually write linear combinations of vectors using I, j, and k. We're going to do something very, very similar. Okay, so let's say, for example, we have in component form, we've got the vector 2, -1, 2. Okay? Now, what we're going to do, what we need is because we're in 3 dimensions, we're going to need 3 standard unit vectors. Okay? And what we'll do is we'll generate them the same way that we generated the standard unit vectors when we did them for 2D. So, we're going to have I, but I is in 3 dimensions now. And so I is going to have an x, a y, and a z. I, though, will only have an x component, so it's going to have a 1 in the x value, a 0 in the y, and a 0 in the z. Then we'll have j, and j is going to have a 0 in the x component, a 1 in the y component, and a 0 in the a 0 in the z. And then k is now our third standard unit vector. We'll need 3 of them to actually generate all of our 3D space. You're going to see that if you do a 4-dimensional space or a 5-dimensional space, you're going to need 4 for a 4-dimensional space, 5 for a 5-dimensional, and it makes sense because you're going to have 1 for every single one of these components, right? If you've got an x, y, z, or a w, x, y, and z, you're going to need components for w, 1 for x, 1 for y, and 1 for z. So our k is now going to be 0, 0, 1. So it's actually really quite simple to write our standard unit vector, okay? We just go through here and we're like, okay, cool. So I'm going to do this standard component, the vector written as a standard, okay, in standard unit form, which is what you're going to see. Standard unit form is going to be then, take the x value, 2i minus 1j, because you've got the -1 for the y component, plus 2k. And each one of them's got this hat that actually represents that we're looking at a standard unit vector. So What you want to see here is that if you take 2 times 1, 0, 0, minus 1 times 0, 1, 0, plus 2 times 0, 0, 1, okay? Algebra in 3D is going to work very similar to algebra in 2D. So what we do is you'd multiply by the scalar. This is once again a scalar, so this is 2, 0, 0, minus 1, or excuse me, minus 0, 1, 0. Or let's make it plus negative 1, 0, 0, negative 1, 0, plus 0, 0, 2. And when we combine all of those together, we've got 2 plus 0 plus 0. We've got 0 plus negative 1 plus 0. And we've got 0 plus 0 plus 2. So we end up with 2, negative 1, 2. And you can see that actually it ends up being the same exact vector. All right, we actually end up with the same vector. What's happened here is that we basically just broken up the vector into pieces. That's what happens when we write it as standard unit form. When you get into linear algebra, these are going to be called standard basis vectors, and they're going to become really handy for us to be able to do, computation, to visualize spaces, okay? And so we're going to kind of use them a little bit now inside of Calc 3. All right, let's do it again. Let's write in standard unit form. And so what we'll write in standard unit form is we're going to take the vector negative 3, 5, 2. And that very simply is going to be then negative 3i, because your x value is an I, plus 5j, your y value is a j, plus 2k. And there it is. See? You can do this. All right. Rock it. So that's how we utilize standard unit vectors. Now, what we're going to do now is we're actually just going to do some algebra. It's going to very much piggyback on what we did for in 2D. So now let's look at algebra for 3D vectors. And what we'll start out with is we'll start out with scalar multiplication. Remember, a scalar is simply a number that either compresses or it expands a vector, okay? And it works like multiplication. In fact, it works like distribution in a lot of different ways. So let's say, for example, I've got 3, and I multiply it by 1, negative 1, 5. What I'm going to do in order to scalar multiply is I'm going to multiply each component by 3. So this is going to be 3, negative 3, 15. There it is, there's scalar multiplication. Yay! We can actually reverse it. Say, for example, I have 6, negative 22, and 41, or excuse me, and 42. What I can do is I can actually factor out a scalar, and I get 2, and it'll be times the vector 3, negative 11, and 21. Okay? So either we can kind of distributing in by multiplying each term by the scalar, or we can also divide out and basically factor. All right? And this is going to actually be kind of handy when we do some other things too. Okay? So let's try it out. Let's try out. I've got 5, okay? And I've got 2, 1/2, and 7. Go ahead, pause for a second. Write it out. We should end up with 10, 5/2, and 35. Okay? What if, like, say, for example, we want to factor out. Let's factor out a 3. And what we have here is we have negative 6, negative 24, and 15. What we'll do is we'll factor out a 3. We'll factor out the scalar of the 3. And we'll end up with 3. And we'll multiply it by negative 2, negative 8, and 5. And that's how scalar multiplication works. Next up, we have addition. And addition is going to be it's exactly the same as it is in 2 dimensions. We're going to add component-wise. So for example, let's say I have 1, negative 1, 3, and I want to add to that 4, 2, negative 1. What I'll do is I'll add the x components. So I've got 1 plus 4. Okay, 1 plus 4, that's 5. Negative 1 plus 2, that's 1. And 3 plus negative 1, that's negative 2. and there's my addition. There it is. There's addition. That's how it works. That's all. That's all we need. Now, what we can do is we can actually combine scalar multiplication and addition to create something called a linear combination. And linear combinations are actually really quite powerful and quite important for working with linear algebra, okay, and for also working with vectors in 3 dimensions. What they are basically is they're a combination of scalar multiplication and addition. Okay, so like say for example, if I take 3 times 2, 1, 2 minus 4 times 4, 2, negative 1. This is called a linear combination. It's called a linear combination because what we're doing is we're multiplying these linear vectors by scalars, okay, and then we're adding them. I know it looks like a minus, but actually addition and subtraction are kind of the same thing when we think about them mathematically. So what we'll do here is we'll actually combine these two. We're going to get 6, 3, 6. That's the first one. And then we'll subtract, or we can add negative 16, negative 8, and 4. Okay, just by multiplying by negative 4. When we add those together, we end up getting negative 10, negative 5, and 10. And that is the result of that linear combination. Now, the thing about it with linear combinations and the resulting vectors from linear combinations is that sometimes we want to write them as the combined vector or the component vector. That's totally fine. Okay, for a lot of purposes, we're going to be doing exactly that. But you should understand when we talk about linear combinations that sometimes we want to actually write them in this form, okay, because it gives us a lot of information. And so we're getting to a point in mathematics and inside of your mathematics career where the information that we get from what we see is actually going to be just as important as the answer or the final result, right? We actually are going to be breaking things down. We're going to see them. We're going to look at them and observe them. And sometimes this form here really gives me a ton of information that I can in fact work from. So the next thing you want to look at is we now want to look at algebra in a standard unit form. One of the things you're going to notice is that we don't utilize the linear combination form or like scalar times the standard unit form plus the scalar times the standard unit form. And a lot of that is because actually the standard unit form is itself a linear combination. Okay, so like for example, let's say I have 3i minus 2j plus 4k. What we forget is that I, j, and k are all actually vectors in component form. So really this thing here is 3 times 1, 0, 0 minus 2 times 0, 1, 0 plus 4 times 0, 0, 1. So that actually is a linear combination. This is the first vector. Here's my second vector, and here's my third vector, and these are scalars. Okay? But we can actually do scalar multiplication and addition with unit algebra and standard unit form. Really not all that hard. Let's say, for example, I want to take 5 times 3i minus 2j plus 4k. That's going to end up equaling 15i minus 10j plus 4k. Essentially, all we're going to do is we're just going to multiply by these scalars. And that's actually a distributive property, okay? So basically, what you can do is, since we're multiplying a scalar times a scalar, you can distribute in the scalars, all right? So basically, like if you wanted to rewrite this, this is essentially 5 times 3i minus 5 times 2j plus 5 times 4k, and there you go. That's exactly what's happening here. Okay? Let's take a look at like what if we wanted to factor out. That's totally an allowed thing to do because sometimes maybe you even want to like divide out, do some, kind of algebra. So let's say, for example, that I've got negative 7i plus 49j minus 84k. And you can see that each one of those scalars, 7, 49, and negative 84, they're all divisible by 7. So let's factor out a negative 7. We get negative 7. And what we'll end up with then is I minus 7j plus 12k. And that's an equivalent form in our standard unit form. And there we go. Addition. Addition's going to work the same way. We're going to actually add the scalars now. Okay. So add each component scalar, and then, kind of bring everything together. So for example, if I look at, I've got 2i minus 4j plus 6k, and we'll put that in parentheses, and I'll add to that another vector in component form. I've got 3i plus 4j minus 4k. What I'll do is I'll just combine my component, the scalars in front of my i's, the scalars in front of my j's, and the scalars in front of my k's in order to create a single component form. So that gives me 2 plus 3i minus, or plus, let's do negative 4 plus 4j, and then plus 6 minus 4k. This is j here. This should be on the outside, j. And so what I get now is I get 5i. This is going to become 0j plus 0j plus 2k. Now, as a convention, if I have 0 of one of the components in a standard unit form, I can actually just get rid of it. So now I can just rewrite it as 5i plus 2k. 5i plus 2k. Right, and what we have here is we have, okay, there's no j. If I want to write this in component form, I just have to remember that there's a 0 in the j spot, right? A 0 in the j spot. So what that means is that if I wrote this in component form, it would end up being 5, 0, 2. So don't forget, like if you're writing vectors in 3 dimensions, it's got to have 3 components. Right? It's got to have an x, it's got to have a y, and it's got to have a z. Okay? There it is. And so that actually completes for us work with vectors. All right? Some key things that I want you to remember. Okay. All right. So now let's take a look at magnitude and direction, because remember we've got directed line segments that are vectors, and because they're vectors and they're directed line segments, they've got to have a magnitude and a direction. Well, turns out things work exactly the same way. We're going to be working with that distance formula. Okay? And we'll talk a little bit about direction in 3D because it's a little bit different. We're not going to be using trig in the same way. Okay? Instead, I'm going to give you kind of a way of thinking about direction. How do we know 2 vectors, in fact, are in the same direction-ish, right? Okay? So what I'm going to do is I'm going to utilize component vectors, and we're going to start out with magnitude. So let's say, for example, I've got 2, negative 1, 3. Okay? And that's v. And so what do I want to know? I want to know what the magnitude of v is. So the magnitude of v is going to end up being the square root. We'll use that distance formula of 2 squared plus negative 1 squared plus 3 squared, which is the square root of 4 plus 1 plus 9, which is root 14. There it is. So the magnitude of that vector is going to be root 14. Square the x component, square the y component, square the z component. Okay? If we're actually looking at one of the things that, if we're looking at a vector where we got an initial point and a terminal point, right? Okay? I think the first thing you want to do is transform the vector to component form. So I think that's probably the best thing to do. It's just going to make life a lot easier for you as you're working. And then secondly, right, okay, use the formula. Right? And that formula, just in case you've forgotten, the magnitude of v is going to equal the square root of x squared plus y squared plus z squared when we look at our vector. All right? X component squared plus y component squared plus z component squared. Now we can actually also do this when we're looking at a standard unit vector, so in standard unit form. Probably a little bit ahead of me, probably thinking to yourself, my goodness, if all of vector calculus is this easy, I'm good to go. So let's say, for example, I've got 2i minus j plus 3k. Well, and that's my v, that's my vector v. So the magnitude of v then is just going to be, well, this is the x component, okay, in standard unit form. So it's going to be the square root of 2 squared plus negative 1 squared plus 3 squared. We've already seen that that is then the square root of 14. Good to know that actually they have the same magnitude because they are in fact the same vector, right? This vector here, this first one we have, and the second vector here, they are in fact the same vector, just written in different forms. You're going to see a lot of that, actually. If there's anything that's really confusing about Calc 3, it is that there's just so many forms. There's so much like new notation, and there's new ways of thinking because you're working in 3 dimensions. But once you kind of get past that, not get past it, but once you kind of master it, then it actually kind of looks exactly like Calc 1 and Calc 2 in many ways. Not exactly, not perfectly, but in many ways. So the last thing I want to talk about is I want to talk about direction in 3D. And so we're not going to get like a concrete way of thinking about like, oh, what's the angle off of this? I mean, we'll do some things like that. But what I really want to look at here, or I really want to like kind of work with, is I want to work with this idea of what we call scalar multiples. Because this is actually going to be kind of a handy way of thinking about vectors and thinking about directions in vectors, and kind of thinking, okay, there's this expansive way of working with vector calculus that maybe you may not get exposed to. So let's say that 2 vectors, v and w, are going to be in the same direction if they're scalar multiples of each other. And this kind of makes sense because what it means for 2 vectors to be scalar multiples is that the first vector, right, is either the second vector or the second vector is the first vector either compressed, right, made smaller, or stretched. Okay, it's either stretched or it's made smaller, and so consequently they've got to be in the same direction. They're just different magnitudes. Same direction, different magnitudes, because all we're doing, we're not changing its direction when we multiply by a scalar. We're only stretching, okay, or compressing. All right, so what that means for us is that these 2 vectors, they're just, if they're scalar multiples of each other, they're actually in the same direction. Let's imagine this just in 2D. Okay, we got 2D, and let's say, for example, this is our vector, that's vector v, and if w is a scalar multiple of v, then v, let's say this is w, notice that w is still in the direction of v. It's just v but longer, okay? It's v but longer, okay? And if you think about that, this is the definition of a scalar multiple, right? It's just the one vector stretched. On the other hand, let's say, for example, I have the vector y, okay? And it's in the other direction, okay? That it's actually in the opposite direction. It's pointed in the exact opposite direction. It's actually a reflection. It is a scalar multiple, and for our purposes, we're going to say they're basically in the same direction, right? Okay, like that reflection, okay, one way to think about that reflection is that it's in the same direction, but that it's being multiplied by a negative scalar, and so it's all on the same, like, basically line of vectors. So if we were working in 3 dimensions, okay, and we imagine we've got this vector here, a scalar multiple of that vector, right, would just be, it'd be in the same direction, it'd just be longer, or it might be shorter. Okay, or the scalar multiple might actually just be pointing in the exact opposite direction. So what does that look like algebraically? We can actually kind of tell this from our vectors. Okay, so if I've got, let's say for example, I've got these 2 vectors. I've got 2, 1, 2. Okay, and I've got 6, 3, 6. What you want to notice is that 6, 3, 6 is equal to 3 times 2, 1, 2. So 6, 1, 6, or 6, 3, 6, excuse me, 6, 3, 6, and 2, 1, 2 are scalar multiples of each other. And from a geometry perspective, that means they are in the same direction. They have the same direction. Okay? That's it, right? One's just longer than the other. And although, in certain cases, like the negative, like a reflection of a vector might be kind of different and might have a different interpretation, that negative direction is also basically the same direction, right? If we just flip it over the origin, we are still moving basically in the same direction. Okay, so this is when we talk about directions in 3D and directions even in 2D, right? Because we can do the same thing and we have the same definition. Say, for example, I've got 5 times 1, 4. That equals 520. Okay, and that means that 1, 4, and 520, they're scalar multiples. Okay, and that also means that they are also in the same direction. So we can actually do that with 2D as well. We can do that with 3D. We can do that with 2D too. Okay, so that's another way of thinking about direction for us, and it's going to go along with the work that we do with magnitude. Okay, so what we've done now is we've basically kind of covered all of our bases when it comes to vectors in 3D for the moment being. We're going to expand on it a lot, but these are the basics. So when we look at vectors in 3D, this is what we talked about. First, we talked about that vectors in 3D, they all have 3 components. Not 2, not 4, not 5. Vectors in 3D have 3 components. Okay, and we'll get a name for it actually soon enough, called R3. All right, and how do you know that they're in 3D? They've got the X, the Y, and the Z. Okay, every vector's got direction and magnitude. In this one, we talked about the distance formula in 3 dimensions and how that just translates directly to figuring out the magnitude of a vector. We've got our standard unit form, which now has our I, our J, and a K. Okay, each I, J, and K in 3D has the 3 components. Okay, we talked about our algebra for 3D vectors. We talked about scalar multiples. We talked about factoring out of scalar multiples and also adding. Okay, and then we talked about these special names and these things that you want to kind of file in the back of your mind, the idea of a linear combination and the idea of a scalar multiple. Okay, so that finishes up our conversation for vectors in 3D.